Hey folks, this is Praveen and today we're gonna solve the lead code problem valid binary search tree. The problem statement says given the root of the binary tree determine if it's a valid binary search tree. A valid BST is defined as follows. The left subtree of node contains only the node with the key less than the node's key. So that means like whatever the nodes are there on the left hand side, all the nodes should be less than the current node. And similarly whatever the nodes are there at the right hand side, they are should be greater than the root node, and this has to be followed by the entire search tree. So then only the tree will qualify as a binary search tree. Now we'll see the example one is given, which is having 2 on the root. The left node is 1, which is less than the root node, and right node is 3, which is again the greater than the parent node. And if we'll see, there's no sub element, so this is qualifying as in like this is a valid BST. And if we'll see here, it is mentioned as true. The second example is given here. If we'll see, the 5 is at the top. If we'll see on the left, we have 1 which is less than the our parent node, which is correct. Now if we'll go on the right hand side, we have 4 which is not greater than 5. That's why this is not a valid BST. And you will see it's returning the false. Apart from this, I would also like to share one more example here. So we can try to understand this by another example. So here we can see I have a tree. 5 is the root node. The child of the left child is smaller than the 5. The right child is the greater than the 5, which is correct. Then again, we'll again check the subtree of the 8. So we'll see the 8 is smaller than, sorry, the 6 is smaller than the 8, and 9 is the greater than the 8. But if I'll make a little tweak, if I'll make it 4, now if we'll see, the 4 is smaller than the 8, but it is also smaller than the 5, which is not correct, because so the definition said all the node on the right hand side should be greater than uh, the root node, or the all the right child of a tree should be greater than. So how we're gonna solve it? So for this, we can have two variable. Let's say uh, minval and maxval. We'll maintain these two variables, the two integer, I would say, and we'll like check the values with each node. So initially both of these would be null, right? Both of these would be null. When we'll check, when we'll come to the root node, we'll check if both are null, and then I think we are on the root, then we'll not check it, and we'll move forward. Since we are going on the left side, so we have a constraint now. We have a max value. So whatever the uh, values or the node will come on the left hand side should always be less than our max value. So here, since 2 is less than 5, we are good. Now again, since we don't have any child node, we'll again go back here. So here our earlier condition was the null. Now we'll check the 8. Since we are going on the right hand side, now we'll be having our main value. Main value would be 5 here. So our node, whatever is coming here, should not be less than 5. Now we'll see like, okay, 8 is greater than 5, then good. And there's no max capacity so far, so it could be any value. So 8 is fine here. Now we'll go on the left hand side here. Since we are going on the left hand side, it has a max value, which is uh, 8. So it should not be greater than 8. And we have already set min value, which is 5. Now this element, since it is less than the main value, that's so we can return here as in false. So that's how we can solve the BST problem. Let's try to write the code for it. So I'll create a helper function for this. Let's say public boolean, uh, we'll call it helper for now, which will going to return the boolean. Now we have a will pass here as the tree node. Then as we saw, we need two variable, minval and maxwell. I'm taking as the integer, not int, because we have to pass null also. So we'll use integer, and I can give here minval integer maxwell for the max check. Now this is our function. First thing we'll check if what is if root is equal to null. That means we reach at the bottom of the tree. So we can, and we didn't encounter any issues, so we'll return true here. Then what we're gonna do, we're gonna check if uh, minval, we use capital minval is less than it. First of all, minval should not be equal to null, and if it is not null, then only we'll check minval is less than equal to root dot val or maxwell is not equal to null, and maxwell is greater than equal to root dot val. Sorry, the condition should be reversed. If min is greater than the current value and max is less than the current value, then we should return false. Otherwise, we'll continue toward the left subtree and the right subtree. To do so, we can call our helper function. So we'll use the recursion. What we're gonna do here, we'll call root dot left, and when we go on the left hand side, what we do, we update our the max value. So our min value would remain the same, and our uh, the max value will be the root dot val. And we'll have to do the same thing for the uh, right subtree. Root dot right. So here now we have to pass the min val as in root value, and the max val remain the same, and we can return it. So now let's use this here, call it from our main function. So from here we'll pass root as it is, and initially we'll pass null and null for both left and the min val and the max val. If I have written it correctly, it should work. Let's try to submit this. All right, so I'll have to return here. Let's try to submit it again. Yeah, this seems working, and the good part it is 100% faster than the other code submitted. So that's how we can solve the binary search tree problem. And this question generally asked by many companies in the interviews. This is a very basic question for like if they want to evaluate on the tree side. So please go through this, and if this video helps you, please like and subscribe to the channel. Thank you.